Hello everyone. Today we're going to look at this contest math problem about complex roots. This is the 2020 AMC 12B number 17. So it's a medium difficulty with regards to how the AMC is. So let's look at the question. Question goes like this. How many polynomials of the form x to the fifth plus a times x to the fourth plus b times x cubed plus c times x squared plus dx plus 2020 where a, b, c, and d are all real numbers, have the property that if r is a root, then so is -1 plus I times the square root of 3 divided by 2 times r. And of course, I is the square root of -1 in this context. So, have a go at it yourself, and then unpause the video. Pause the video, have a go at it yourself, and then unpause the video. So, this is how, this is one way to do it. So first, let's look at the -1 plus I times the square root of 3 over 2 part. What is that basically? Well, we can use Euler's formula to convert it into e times I times 2 pi over 3. Now, I'm not going to go over how that works out because at this point, at number 17, they expect you to know a little bit about complex roots and how to convert it from one form to the other. So, I'm not going to go over that right now, but if you do want to know how to do that, just tell me in the comments and I'll do that for you. Anyway, so we find out that this is equal to e to the power of I times 2 pi over 3. And again, just use cosine x plus I sine x or Euler's formula to find that. So what this is saying is that if r is a root, then r times e to the I times 2 pi over 3 is also a root. And then that's a root, right? So we have to multiply that by r times e to the power of I times 2 over 3 to get r times e to the power of 4 I times 4 pi over 3. I'm sorry if I make a couple of mistakes in talking about it, forgive me. But essentially we're multiplying by e times I to the 2 pi over 3 each one. So now if we multiply it again by e to the power of I times 2 pi over 3, we'll go back to r, as you can see, because the e to the power of 4 pi over 3 and e to the power of 2 pi over 3 are reciprocals, so they'll just cancel out with each other and be 1. So we have our three roots over here. However, keep in mind that this polynomial is of fifth degree, so that means there has to be 5 roots, right? So let's assume that there's another root, g. Sorry, I had to scooch my chair a little. So if g is a root, then g times e to the power of I times 2 pi over 3 is a root. And then if this is a root, then multiply it again by e to the power of I times 2 pi over 3. And you get g times e to the power of I times 4 pi over 3. So now we have 6 roots. But this is not good. Our polynomial is of degree 5, and you cannot have more than 5 roots in a polynomial of degree 5. This is, in fact, the fundamental theorem of algebra. If a polynomial is n roots, is of the nth degree, then there are n roots. So we cannot assume that there is another root g. There are only these 3 roots over here. Now you may ask, well, didn't you say that there has to be 5 roots? Well, yes, 5 roots, but that is counting multiplicity. Now, if you don't know what multiplicity is, I won't go into it that much over here, but basically it's the fact that some roots count as a double root. So basically x squared, y equals x squared. Well, since y equals x squared has degree 2, there should be 2 roots, but the only roots for y equals x squared is x equals 0. So that means that there are 2 roots in y equals x squared, it's just that there's a multiplicity of 2, meaning that one root accounts for 2 roots. So anyway, we have these 3 roots, r and then these over here. So after that, we can just convert these 3 roots into the polynomial by doing this. X minus r, one of the roots, to the power of some m that we don't know of, times x minus r to the power of I times 2 pi over 3 to the power of another n that we don't know of, times x minus r to the power of I times 4 pi over 3 to the power of p, for which we do not know. Now, again, going back over here, there's a degree of 5 over here. So that means these exponents over here, when they're added up, their sum has to equal 5, where m, n, and p are natural numbers, or 1, 2, 3, 4, 5, on and on and on. If it was a rational number or an irrational number of some sort, like a fraction, then this whole thing would not make sense. These roots the exponents have to be integers, and if they're 0, it doesn't really make sense, because that means it wouldn't be a root in the first place. So we say, oops, sorry about that. So we say that it has to be in the natural numbers. So we're taking away 0, so it's just 1, 2, 3, 4, and 5, on and on and on. 1, 2, 3, 5, 6, 7, 8, 9, 10 plus. So again, m plus n plus p has to equal 5 because of degree 5. So now you may be thinking, well, all we have to do is just find all m, n, and p for which the sum equals 5. Well, hold on. One really important thing that a lot of people probably forgot is this right here. A, B, C, and D have to all be real numbers. A, B, C, and D in this original polynomial. Now, what does that mean? Well, that means that these exponents have to abide to certain rules. What that is this over here. These roots. When you multiply them together, this whole polynomial, you cannot have any i's. For instance, there's an I over here and an I over here. We want these i's to cancel out because we don't want any i's in the when we FOIL them all together in our original polynomial, as you can see over here, right? So what do we do then? We'll notice something. Hopefully you can see over here. E times e to the power of I times 2 pi over 3 times e to the power of I times 4 pi over 3 is, just add the exponents together, e to the power of 2 pi I. Now, and e to the power of 2 pi I is equal to 1. Now, if you don't know that, you have to learn a little bit more about Euler's formula and complex roots. But for now, I'm just going to assume that you know that e to the power of 2 pi I is equal to 1. So we want these roots, when they're multiplied by each other, to be equal to 1. We want the imaginary numbers to cancel out. And the only way we can do that is if these exponents are the same. N, as in Nancy, and P. These exponents have to be the same, because then you have an equal amount of this root and this root. So when they're multiplied together, they'll cancel out the imaginary part. So what does that mean? Well, now we just have to find all m plus n plus p equals 5 for m, n, and p being natural numbers and n being equal to p. So now this is pretty easy. Let's just figure out one value for m, as in Mary, 1. So if this is 1, so subtract 1, that means n plus p has to equal 4. So that means each n and p has to equal 2. And we have one solution right here. One solution down. Let's see, if m was 2, well, that wouldn't work, because then n and p wouldn't be natural numbers, because subtract it, you'll be n plus p equals 3. And there are no natural numbers for n equal to p that will equal 3. So 3 doesn't work. Well, what about 3? Well, if we subtract 3 on both sides, we get n plus p equals 2, and that's pretty easy. That's just 1 plus 1. So we have 3, 1, and 1 as another solution. Let's just go on and see, if m is 4. If m is 4, that means n plus p equals 1, which, if n and p are natural numbers, will not work out. And then obviously 5 wouldn't work out either, because we're looking at natural numbers, so we're ignoring 0. So that is our answer. We have one solution over here, another solution over here. There are 2 solutions which abide to this question right here. And that's our answer, 2. Now, just a little commentary on this question. I did explain a lot of things, and the question, when I explained it, took about like 9 minutes. So if you're trying to get into the AIME, then number 17 is pretty much the last question, usually around the last question that you're going to look at and try to answer. So this question is actually not that bad in a conceptual manner. In a computational manner, but in a conceptual manner, it is kind of difficult because you do have to know some facts. But we still get number 2 over here, and we are done. Thanks for watching.